Beneath this sheet lie the remains of a person. But who were they and how did they die? By examining the details of these remains, what we hope to do is to reconstruct a life and to reconstruct a death. How did they live and how did they die? Good evening and welcome. This is the first of 3 Christmas lectures from the Royal Institution, revealing how forensic scientists use a range of tools to help to investigate and bring criminals to justice. In this first lecture, I'm going to show you how forensic anthropologists, such as me, study human remains to uncover the stories that are written in our body and our bones. I'm Sue Black and I'm a forensic anthropologist. And in my career, I've been involved in war crimes investigations, in mass fatality events, and in cases of suspicious deaths. My job is to examine what remains of the person and through that investigation to confirm who they were in life. Because without a name, it's really difficult to investigate a crime and to determine if a crime has been committed. You might have seen forensic scientists on programs on TV, and we got a special guest this evening. What I'd like you to do is give us a really warm welcome for Amelia Fox. Amelia. Twins, but we're trying really hard. Amelia, thank you so much for joining us this evening. I'm really grateful to you. Now, you will all know, I'm sure, that Amelia plays the character Nikki Alexander, who is a forensic pathologist in the hit BBC show Silent Witness. And Amelia, there are lots of forensic experts out there. I'm a forensic anthropologist and you portray a forensic pathologist. Mm-hmm. The difference between that being, I'm usually looking at people's identity and you're usually looking
for the manner and cause of someone's death.
So you get the really exciting stuff, is what it amounts to. Now, when you took on that role, did you have to do research?
Oh, yes, absolutely. I observed 2 real postmortems and seen the immensely skilled work of pathologists who go through each and every part of the body looking for clues as to the cause of someone's death.
Was that challenging for you to look at those?
Well, I was a bit scared about whether I was going to faint, and I put my scrubs on thinking, well, at least I can pretend to be a pathologist in the room. And the first post-mortem that I saw, he was of an old man and he died of natural causes. But what really struck me was that we can still tell so much about a person's life and how they lived it, as well as what caused their death. And the second post-mortem that I saw was of a young man, and his life had been cut short far too early. And that made me think we need to make the most of every day.
We do, don't we? And that's a really important fact, I think, for us to all hold on to. So what we're going to ask you to do, if you don't mind, is we're going to ask you to do a little bit of a game with us, to look at some of the remains we've got here, taking some of our audience here to help you. And the question is, are the remains we're looking at human or animal? Can we tell the difference? And we're going to start with this one. So you might like to take that and you might like to show it perhaps over on this side. And what we're looking for, do you think this is human or do you think it's animal?
Okay, what do you think? Human or animal?
Animal.
Animal?
Okay. Why do you think it's animal?
Because it's like shaped weirdly.
Why is it an animal?
Nails?
Yeah, they're quite long. This is so skinny.
So long nails. Have you never been to a nail bar? Yeah, you can get really long extensions on your nails, can't you? Animal? Animal?
Definitely.
Does anyone think it's human? Oh, you're far too good. It is an animal. So what it is it's a seal flipper. And so frequently, because we were surrounded by sea, all sorts of things get washed up on the shore. And so we will get a phone call from a police force that will say, member of the public's phoned in, they found a human hand on the beach. No, they haven't. What they found is a seal flipper, but we can't always be certain of that. So we will go away and check. And then we usually say, what did you do with the seal flipper? And they say, oh no, we threw it back in the sea. Don't do that because the tide brings it in twice in the weekend and we see the same seal flipper over and over again. So well done. If you said that was animal, well done. This one we're not going to ask you to move. It's a bit heavy. Is it animal or human? Animal. Does anybody think it's human? No. I know you're teasing me. So that it's obviously a very large boar.
A boar?
A boar, yes, as in a wild pig.
Right.
And the skull is the most easy part for us to determine if something is human or animal. But of course, we don't always have the skull. So what about if we had something really tiny like this bone?
That's much harder.
That gets much harder, doesn't it? So maybe you'd like to take that, if you would, Amelia, and maybe up into this corridor up here.
Right, good luck, everyone. This is a much harder task.
Is this going to be human or is this going to be animal? What do you think? Human or animal?
Animal.
Animal?
We've got lots of people saying animal up here.
We're going to take animal?
Yes? Human. Human. We've got one person thinking it's human.
Doesn't it show that it isn't always as easy as you think? And in fact, most of you who said this is animal have got it wrong because it is human. So very well done.
And where's it from?
It's from this part of the hand. So it's from a metacarpal, which is this second one on the index finger. It's also very commonly compared to bones of a horse's tail, for example. So it's very difficult sometimes to tell those apart. So that one we didn't do so well with. Let's try this one, because I think this probably looks like a bone that most people would recognize.
I think that might be from a leg.
Oh, well done. You have done pathologist training.
Okay.
So up onto this side, if you wouldn't mind. So it's a leg bone. Is it a leg bone from a human or is it a leg bone from an animal?
Animal.
Animal? What kind of animal do you think it might be?
Dog.
Go no further. Well done. Spot on. A future in forensic anthropology. I'm out of a job now. Well done. So this is the thigh bone, the femur of a dog. And because it's doing the same function in the human, they look very much the same. So I wonder, are we ready to have a look at what's underneath the sheet behind me?
I am.
You are.
Are you guys ready?
Are you ready?
What's
Do you want to
underneath?
see what's under here? We're going to take it off very gently.
Animal or human?
Ah, well, there's a question, isn't it? So, it's not just a pile of bones, though, is it? It is a human being. And because it's a human being, it needs to be treated with respect. This was somebody's son, somebody's daughter. We need to remember that at all times when this is in the room, it is another person. It's not just a pile of bones. So, what we're going to do for the rest of this lecture is we're going to reconstruct who this was. We're going to learn a bit about the life history, and I'm hoping that at the end of it, we're even going to be able to see what they look like. So, it has at the moment just a number, and that number is SK, which is the skeleton, and 2057. So for the moment, 2057 is all we have. Let's see what we have by the end of the lecture. Very best of luck with the next series when it comes.
Thank you.
Amelia,
good luck with the
thank
identification.
You. Thank you. Thank you. When we try to identify someone and what makes us memorable, we need to look at what it is that we remember somebody by. When some of you sat down in your chairs, there might be a mirror that was placed on your chair. Have a look in it. What do you see? You see your face. And isn't it a beautiful face? It's the one you woke up with this morning. You haven't changed it since. Everybody recognizes you because of that face. And when you look at the human body, there's two parts of the human body that are almost always in view to us. And you can see it in yourselves. We can see your face and we can see your hands. And in another lecture, we're going to come back to looking at identification of the hands. So what I'd like to do is I'd like to welcome from the Face Lab at Liverpool John Moores University, Professor Caroline Wilkinson and Dr. Jessica Liu. Caroline, thank you, Jessica, for joining us. Caroline, would you tell us the process perhaps that you go through, what it is that you do, and then how you go about it?
Yes, so when the police can't identify human remains, they will sometimes come to Face Lab and ask us to produce a facial reconstruction, and that image will be released to the public in the hope that somebody will recognise the individual, and that will then help with identification. The fundamental premise behind facial reconstruction is that our skulls and our faces are directly related to each other. So the skull provides the proportions and the shape of the face, and as your facial muscles grow and develop, they leave their marks on the surface of the bone. So we hope to be able to look at a skull and interpret it and predict the living appearance of an individual. But it's a digital process. This is our laser scanner. It projects light onto the surface of the skull, and cameras collect that data and put the images together to make a full 3D model of the skull of the individual.
So clever.
So when we've got the fully scanned skull, we can then take that into our computer system. We can see the 3D shape of the skull, and the blue areas are the areas that were missing that we've remodeled. We then use tissue depth pegs to help us estimate the amount of soft tissue over and above the muscles. And then we have a database of anatomical structures, mostly muscles, that we import for each skull, so that we're slowly building the muscle structure onto the surface of the skull and building the face from the skull through the muscles to the surface of the skin.
What you used to do is you used to be able to mould on with clay, didn't you?
Yeah, that was the traditional method, and now we can do it all digitally in the computer. So what we have here, because the most frequently asked question to me is, how accurate is this? We can do that using living individuals. So this is a test that we produced a number of years ago. A volunteer gave us his computed tomography, which is clinical imaging that you might get in a hospital. We could then take his skull without knowing what he looked like, produce the reconstruction that you can see at the top. This is his actual face from the scan on the bottom. And then what you're seeing here is a comparison of those two surfaces. So we can see where the errors are. The blue areas are the areas with the least error, and the red, orange areas are the areas with the most error. About 70% of the surface of the facial reconstruction has less than 2 millimeters of error.
And you scanned all the different parts of this skull.
We have.
And I'm hoping you're going to come back and you're going to show us what the face of this individual may look like.
We will.
Now, I've not seen it yet, so you and I are going to see it for the first time later on this evening, and I can't wait. So Caroline and Jessica, thank you so much indeed. Thank you, and I look forward to seeing you later. So how are we going to tell whether this individual died recently or a long time ago? Now, sometimes it's about how the body looks, and sometimes, I'm afraid to say, it's about how the body smells as well. So something that's decomposing, as I'm sure you can imagine, doesn't smell terribly well. So that we're going to use that to try to estimate something that's called a TDI, or a time-death interval. And so that will allow us to determine whether this is something that needs to be looked at by the police or needs to be looked at by an archaeologist. And the cut-off point between those two is 70 years before the present date. So if you died 71 years ago, you're technically archaeological. If you died 69 years ago, you're technically forensic. And it's all based around the fact that man is expected to live 70 years and 10. And when you take back that 70 years, that takes us back to 1952, just after the Second World War. So that bodies that we find from the Second World War or before are technically archaeological. Now, I can tell you quite safely that our body here is not going to be recent. The bones are very dry, they don't smell at all, or you'd know about it sitting so close to it. this is going to be a body of somebody who's died a very long time ago. Now, we need to look at some features of decomposition to determine how much time has passed since death. Now, I want to show you decomposition in action. One of the things that's really important and that affects decomposition is insect activity. So if you're a little bit squeamish, look away now, and I'll tell you when you can open your eyes again, because we're going to look at a video. And we're going to look at a video of a specimen of a fox head, and that fox's head is going to decompose using dermestid beetles. And these are flesh-eating beetles, and they live perfectly normally in our soil every single day. There's our fox. Can you see the beetles starting to move? Can you see the fur starting to shift? Look at the fluid that's starting to come out from the head. You can see the fur starting to pull away, clearing off all that soft tissue so that underneath it you have the white bone. You can open your eyes again. Our individual is dry and has no smell. And it is not, I promise you, going to be of any interest whatsoever to the police because it is clearly archaeological. So let's start to build up a picture of who this person may have been in life. And what we will do is we'll develop some of the characteristics that you would expect to hear in a police bulletin. A male, aged between 25 and 30, 5'6" to 5'8" in height and white. Those are the sort of main characteristics, and we call them the Fab Four, because we can look at sex determination, age determination, the height of an individual, and what is their ethnic origin. So let's start with the first of these. How do we determine if a skeleton is masculine or it's feminine? Now, what I want to have are two volunteers, and I will certainly look at this young lady here and somewhere this gentleman here. Thank you very much indeed. If you come down. Your name is?
John.
John and?
Anna.
And Anna. And what we're going to do with John and Anna is we want to be able to look inside them. So we want to see what your bodies look like inside. Are you okay with that? Thank goodness for that. So what we're going to ask you to do is to go behind the screen, okay, round the other side of the screen. And Anna, I'm going to ask you to come to this side here. Now, we want to be able to look inside them. And what would we use to look inside somebody? We'd use an X-ray, wouldn't we? Of course we would. But we're not going to do that to you because an X-ray wouldn't be safe. But we're going to do something a little bit different. We're going to show you what your skeleton looks like. So we're going to do it on the countdown from 3. Are we ready? 3, 2, 1. There you go. That's what you look like. Now, we can all see what you look like inside. Would you like to see what you look like inside? Come on round and have a look. So what we've got there is amazing. You came round and your skeleton stayed there. It's incredible. What we've got is a male skeleton, a female skeleton. Can you see any differences between them, do you think?
Yeah, the male one's a bit taller than the female one.
And it's maybe a little bit bigger. The bones are a bit bigger as well. What about the female one? Can you see any differences there?
The pelvis is different.
The pelvis is a bit different, isn't it? So we can see some general differences. And we know that most of the general differences that we find in relation to the male skeleton are to do with levels of testosterone, because what they do is that they affect muscle, and muscles need some really robust bone to be able to attach onto. So they tend to be bigger and taller. And when we see the changes in the female, what we're looking at are the relationship between the bones and estrogen, which is a feminizing hormone. And we see those changes happening in the pelvis. So thank you both very much indeed. Thank you for letting us look at your body. Thank you. What we need to do now is we need to look at something a little bit more specific. And here we have some specimens. Thank you very much indeed. So, on this side, what we have is we have a male skull, and on this side we have a female skull. We're going to look at this area just above the eyebrows. If I turn that around, can you see that there's ridges across the top of those eyebrows? That's a masculine trait. If we look at the feminine skull, then they don't have that same level of bridging. It's only going to develop when you get towards the end of teenage years. And it's all to do with the muscles associated with chewing, and they dissipate up across the face. So we find that bridging in males, we don't find it in females. And right behind your ear, there's a lump of bone sits behind your ear here, and it's called the mastoid process, which is this one there. And it's got a big muscle with the most ridiculous name called sternocleidomastoid that attaches to that. And because it's a much bigger muscle in men than women, it's a much bigger bump in a male skull than it is in a female skull. And then at the back of your head, there is a bump right at the back of your head if you're masculine. And that's got an equally ridiculous name. It's called the external occipital protuberance. You remember that one, and you'll impress everybody at Christmas lunch. What that does is big muscles from your neck attach there. And your head's something really incredibly heavy. And if you're in any doubt, watch somebody who falls asleep on the sofa. Watch their head suddenly fall forward like a nodding dog. It's because the head's so heavy and the muscles have got to hold it up. We have this really well-developed occipital protuberance there. And if we can have a look, if you could hold it for me, Isla, that would be much appreciated. We just don't have that same level of bump on the back. So we can look at the skull and tell the difference between a skull, thank you, that is masculine and one that is feminine. But in the pelvis, we have something very different. The male pelvis is quite childlike in terms of its development. And we want to see it change at puberty in the female. And we're going to want to see the pelvis change and grow from side to side. We're going to want to see it change and grow from front to back. And we're going to want to see the whole of the pelvis lifted up from the back. All of that happens in 3 or 4 years. How amazing the way the skeleton can change. Why does it do that in the pelvis? Why do we see changes in the pelvis compared to the female rather than the male? Red jumper.
Because as females develop, they need to be able to carry a baby, and so a bigger pelvis allows the baby to more easily fit through.
Absolutely. So we want to be able to see, can we get the baby's head through the female pelvis? Because if you're right, we should be able to. So that the female pelvis, it goes in, and if we get it in, we want to be able to get it out, and we can. So it's a much wider pelvis. Doesn't happen. So it's not changed in shape, it's not changed in size. So what we're seeing in the pelvis are differences that estrogen cause that allow that pelvis to change dramatically in size. So if we go back to our skeleton, what can we find in here that tells us about what sex the individual may be? And I'm going to go to the skull first of all, and the skull is very delicate. So at the front, can you see these brow ridges? And we know that we find brow ridges in males, thank you. If we look at the mastoid process at the side, it's quite large. We find that in thank you very much. And when we look at the back of the skull, look, we've got a lovely little external occipital protuberance, which we find in male. I have a room full of forensic anthropologists. Well done. So that skull tells us, and you've told me, that you think that's a masculine skull. And the next thing we're going to do is to say, well, how tall might he have been? And most of our height comes from which part of our body? The legs, doesn't it? If you've got long legs, you're going to be tall. If you've got short legs, you're going to be closer to the ground. So we've got long bones, particularly in the legs. And what we do, quite simply, is we take those long bones, we'd measure them, and we'd come out with a height. And the height for this individual is round about 177 centimetres, which is about 5'10". Now, bear in mind that this is an archaeological specimen. That's actually quite tall to be 5'10". The next thing I think we need to do in that Fab 4 is we need to look at determining age. And there's one part of the human body that is really very useful for determining age. And what it is seriously, thank you very much indeed for a set of chattering teeth. But teeth are incredibly useful for being able, oh, it's like my daughter, it keeps talking, are incredibly useful for being able to tell us something about you. And we have lots of things that we do to our teeth. We go to the dentist, we have braces put on them, we have fillings put in, we have implants. I have got more fillings than I've got teeth because I've got a good Scottish mouth with very, very bad teeth. And that profile is mine. And a forensic odontologist, which is a dentist, will be able to look at my records and be able to look at my teeth and say that they're a match. Over a lifetime, humans have got 3 sets of teeth. What a set of teeth. They have 3 sets of teeth. And we have baby teeth, or milk teeth, deciduous teeth. We have adult teeth, or permanent teeth. And then we have a 3rd set, which are false teeth. So whether they're plastic teeth or they're porcelain teeth. So we have 3 sets in total. And I'd like to show you a really interesting set of those false teeth. Can you see that these teeth are set in a horseshoe? And that horseshoe is made out of ivory. And we don't know what bone it is or what tusk it is, but it's ivory. And when you turn it over, you can see that the teeth at the back are really quite crude. They're just sort of cut out of that block of ivory. But the teeth at the front are incredibly realistic. That's because they're real teeth. And these were called Waterloo teeth. And women used to be paid to go out onto the battlefields, extract the front teeth from the dead soldiers on the battlefields, take them back to the dentists and sell them. And you could go into your dentist and be shown a chart of teeth, and you could choose your teeth that you wanted to build your set of dentures from. And it just shows the Hollywood smile that we want to be able to get these days. We were still looking for it 200 years ago, but we were doing it in a slightly more grotesque way. Those baby teeth are really important as well, because if you remember back to when you were about 5 or 6 years of age, and this is what a jaw would look like. What you didn't know was underneath that gum margin, and what we've done is we've just cut away all of the bone on this model. Your grown-up teeth were growing underneath there. And so we can see the crowns of the adult teeth developing down in your lower jaw, up in your upper jaw. You didn't even know they were there. And as they grow and they develop their roots, they're going to push the baby teeth out. So we know that we can use teeth to help us determine age. And one of the things that we can find in our skeleton when we go back to it and we look particularly at the mandible, which is the lower jaw, what you can see is although we've lost the teeth at the front, that's just because of the process, it's archaeological. When we look at the teeth towards the back, and these are the molars, there's the first molar, the second molar, and the third molar. And the third molars we call the wisdom teeth. And those wisdom teeth are because they come into your mouth when you're suddenly supposed to be wise. And you become wise when you're about 18 years of age, apparently, which is why they're called wisdom teeth. But you can see there's quite a lot of wear on the first molar, less wear on the second molar, and very little wear on the third molar at all. That tells us those teeth, certainly the wisdom teeth, have not been in the mouth very long. And I told you that they come into the mouth at 18 years of age. What else can we tell about the age of this individual? Well, we talk about 3 phases of aging. So from birth right the way through to the end of puberty, that's where we grow. And then when we get to the end of our teenage years and we get to maybe into our early 30s, we kind of stop growing and we go through a bit of stasis. Once you get beyond your 30s, everything's degenerative. You start to break down, you start to get old, and we start to see evidence of that degenerative change post 30 years. We have no evidence of degenerative change in this individual. 2 areas just that I want to take you to see if we can narrow down his age. This is the sacrum, which sits at the back of the pelvis. And what I'm going to do is I'm just going to take away this little section of bone because it's not broken. It just hasn't fused yet. And because it hasn't fused, I know this individual is under 25. And one more bone, which is my favorite bone. Every anthropologist needs a favorite bone. So if you're going to be one, choose one. Mine's the clavicle. And this is a left clavicle or collarbone. And if you can see along the surface, this is the articular surface around here. And if you zoom in, maybe you can see there's a little flake of bone there that looks as if it's been stuck on with glue. That's a growth plate, and that bone's going to cover the entire surface. But because there's so little of it present, I know this individual was somewhere between the ages of probably 17 and 19 years of age. So this is not an old man. This is a young man between the ages of 17 and 19 years of age. So we know it's a male, we know it's a young male, we know he was about 5'10", maybe 5'11" inches in height. But the bones have got more to tell us. There's still more of a story for us to find. And have you heard the phrase, you are what you eat? Well, we are literally what we eat. And the human body is a recording machine. It lays down all the information. Everything that we eat, everything that we drink, lays down the cells, whether those cells are bones or other kinds of tissue. What I'm going to do now is going to hand over to a colleague of mine who's been instrumental in taking this area of research forward. And I'd like you please to welcome Professor Wolfram Meyer-Augenstein. It is a great name, isn't it? Wouldn't you want to be called Wolfram Meyer-Augenstein? Wolfram, tell us what it is that you do for a living.
I'm a professor for stabilized forensics. I occasionally help out police forces, law enforcement agencies, nationally and internationally, with crime investigations.
So you mentioned the word stable isotopes there. So what does that mean? What are stable isotopes?
How to explain that? Obviously, what your body is made of has to come from somewhere, and that is basically the food you eat, that's the water you drink. And we can, to a degree, track that because nature has given us a marker in our hands, stable isotopes. And I think the best way to describe these stable isotopes are basically atomic twins. These atomic twins are basically identical in virtually every shape or form that you can think of, but they differ in one aspect. They have a different weight. Virtually every element that makes compounds in your body, hydrogen, carbon, nitrogen, oxygen, and sulfur, they all have a twin that is just slightly heavier. And this difference in weight we can measure in the way plants make things. And it also makes a difference for water. And we have actually a map that illustrates this. You see, that is an isotopic map or a landscape of water across the globe. And the differences in how much hydrogen too, the heavier atomic twin of hydrogen is present, is expressed by colors. So what we saw on the global scale, we also see on the regional scale. This is a map of Scotland. Yeah? And isles that basically sit here get the first rainfall. That water that ends up then to be drinking water is heavier in hydrogen too than the water in the canned worms. And these things translate into your tissues. So, for instance, hair. When we analyze your hair, we can actually say, oh, you lived in Norway. You are Norwegian. We can do it in nail, we can do it in bone, even in teeth. And we have actually found a volunteer who very gladly gave up a thick lock of her hair, and there she is. Say welcome to Ayla. And I think the best bit is we let Ayla quickly tell us what happened, how it happened, when it happened.
As you said, it was definitely I volunteered for this, to have quite a substantial chunk of my hair taken from my head and sent to one of your colleagues, I believe, up in Scotland.
Yes, and this is the really decent lock of hair that Ayla donated. So it was cut and sectioned by cutting segments of this hair to represent a fortnight of growth. Because hair grows at a defined rate. It typically grows at 10 millimeters a month. Before analysis, the hair has to be washed and rinsed and dried. And I know it sounds funny, but it has to be done. And this is the result. On the hydrogen, you have basically a kind of a plateau line here and a plateau line here. And the same is repeated throughout all the other isotopes that make up the hair. This drop in between those lines happens between months 8 and 6 relative to the point when the hair was cut. So what we can definitely say from this person lived at 2 different locations along those 20 months that her hair length represented. First she lived here, then she did something we don't know exactly, but she definitely moved away. And then she arrived here and for the last 6 months lived in this area. And if you would ask me where all this happened, I would have to be honest and say, no, I don't know exactly, but I can give you a scientific wild guess. We can basically say, right, my guess would be somewhere on the other side of the globe, Australia, and if you press me very hard, the southeastern coastal area of Australia would be this part from -20 to -8, and from -6 to north. That could be Central Europe, that could be Belgium, that could be Netherlands. It could also be England, especially the south of England, Greater London. The only person who can actually now say if I was talking through the back of my head or if I actually said something sensible is Isla, please.
I was living in the southeastern corner of Australia up until about 8 months ago, and then I moved to the United Kingdom about 6 months ago.
And what did happen in between here?
I was travelling around Central Europe and the Middle East.
Wonderful. So that's great. Thanks very much, Isla.
Thank you.
And
Thank you.
that
I'm
is
behind you.
basically as much as I can. Oh!
Thank you. And thank you, Wolfram, for explaining that. Amazing. Did you manage to have a look at the isotopic signature associated with our skeleton?
I saw the report of the analysis that was basically taken from samples of the femur, because even bones retained information, and there were two sets of data. One was from radiocarbon, which gives you an indication when the person passed away. That came up with roughly 1,000 years before now.
So this skeleton is 1,000 years old?
Yes. And from the stable isotope data, oxygen data and carbon and nitrogen data, they point to an individual that had quite a large element of marine-derived protein, i.e., fish, or maybe seaweed, I don't know, sushi.
They were found in Oxford. There's not a lot of marine fish in Oxford.
Not really, no.
No, so it's not likely this individual grew up there?
Not
Somewhere
even that.
else?
Yes.
Where?
I would say Scandinavia, so Denmark, Sweden, maybe.
So, Wolfram,
Yes.
could our skeleton be Viking?
It could be a Scandinavian warrior.
That's what we want, isn't it? What we've got is we've got a Viking loose in Oxford.
Good. Fine.
That would be great.
Just as well he's dead then.
1,000 years old, Danish background, eating fish, could have come from Denmark.
Yes.
I like it. I like it very much. Wolfram, thank
so
you
glad
very
you
much
like it.
indeed. Thank you.
My pleasure. Thank you. Thank you.
We've got a Viking! Thank goodness for that. Doesn't that make it twice as interesting as it was? Now, listen, what we now want to do is we want to know something about how did this individual die? So we need to look at trauma and anything that might suggest a cause of death. Now, there's three important things that we find around about injury, and that's when they occurred. So we like groups of threes. Injuries are ante-mortem, which means they happened before the person died. And we know that that happens because we see healing in bones. The injury could have happened around the time of death, and we'd call that peritrauma. And that's going to be really important to talk about the manner of death, which is the way in which the death occurred and the cause of death. And the third one is going to be if they're post-mortem injuries. That means it happened after death, maybe when the body was being excavated or being buried. And we're going to look, again, I told you we like groups of threes, for the three types of injuries that we might see. We can have injuries that result from ballistic or projectile trauma. We can look at injuries that result from blunt force trauma, and we can look at injuries that result from sharp force trauma. So first of all, we're going to look at ballistics, and we're going to look at projectile trauma, and we're going to see whether we can find any of those on our skeleton. Please welcome Dan from our demo team, who's carrying an air rifle. It's an ostrich egg.
Okay, can I have the safety marshals in position, please? Safety is off. Firing in 3, 2, 1. Gun is safe.
I have to ask, do you want to see it in slow motion? Yeah. Of course we do. Let's have a look at what happens in slow motion. You can see the laser. So that's where we're going to hit the egg. There's where the shots happened. You can see that fracture head up there. And can you see that there's debris coming out the back? A good shot. And when we have ballistic trauma or we have projectile trauma, what we want to be able to determine is what's the entry wound and what's the exit wound, because that tells us something about where the gun was and the position of the gun. So if you have a look at the front here, this is the entry wound. And the entry wound is when the bullet is traveling at its highest velocity and it punctures cleanly through the bone. And it's punctured just as cleanly here through the egg. When it goes through the content of the egg, then it slows down and it loses some of its velocity. So when it comes out the other end, it's a bit more messy. So when we turn around and we look at the exit wound, look at the nice, neat entry wound, the exit wound is much bigger. And so that we know as the exit wound because it's sprayed out. And it's not expected that in our body we're going to find ballistics because we didn't have guns at that time. But we can find projectiles, and we'll come back to that in a little bit of a moment. But what we want to be able to do first is we want to now introduce the next type of trauma that we might see, which is blunt force trauma. So for blunt force trauma, we're going to cause some fracturing in the bone. And I can show you quite easily what that looks like. But what I do need is a volunteer. Red jumper. Please come down. Just stand here with me. Thank you. And as if by magic, we have another ostrich egg. Your name was?
Noah.
Noah. Okay, so Noah, what I'm going to ask you to do is I'm going to ask you to inflict some blunt force trauma on the egg. And of course, the only way you're going to do it with an egg is with a spoon, isn't it? Now, are you right or left-handed?
Right.
Right-handed. So pick up the spoon for me. If you come round that side for me. What I'm going to ask you to do is I'm going to ask you to hit the egg just once about there, okay? So you're going to have to hit it hard enough to break it. So we're going to go in. 3, 2, 1. Yes! Well done! Very good. Can I just say there's a lovely smell of ostrich egg down here, which is not very nice. Now, that's the impact. And so when you hit it with a spoon, then that pushed it in and it hit the egg behind. And as it bounces out, you get what are called concentric fractures. You can see it going around the impact zone. And that's because they've bounced back. But there's other fractures that radiate out from it, and those are called radiating fractures. So this is classic blunt force trauma that says there's the impact, there's the concentric fractures around it, and there's the radiating fractures around it. Now that's really useful, but there's something else that we can do, is that we can sequence events. So if you were to hit it again, I should be able to tell you which was the first hit and which was the second hit. So I'm going to turn it around to here, and I'm going to ask you if you can aim for about there. Perfect. Thank you very much. Oh, and you couldn't have done that better. So we had an impact, but can you see this radiating fracture coming up there?
Yes.
What happens to it?
It looks like it kind of like joined with the other one.
It stops, doesn't it? And so what's happened is this radiating fracture, with all the force that's coming out of it, suddenly falls off a cliff because there's a hole in the egg. And so it can't jump over that line. And that tells us when a line of a fracture intersects with another one, this was the first impact, this was the second impact. And the more impact you have, the more difficult it becomes and the more complex. Good job. Thank you for blunt force trauma on an ostrich egg. Well done. What I want to do is I want to say, do we have any evidence in here of blunt force trauma? And the answer is no, I don't. So I might have projectile, but I don't have blunt force. So what's left to us? Yeah, go on, shout it. Shout it out for me. Sharp force trauma. So we need to be able to see whether, using a weapon, we can leave cut marks on bone. So to do that, I'm going to need a volunteer, please. Would you come forward for me? Thank you very much. And your name is?
Tilly.
Tilly. So this is Tilly. Tilly, what we're going to do is we're going to try and leave a cut mark on a bone. Are you ready for this? So here comes the bone. And the bone is surrounded by some soft tissue. Are you feeling as confident now as you were 2 minutes ago? We're going to have to cut through the soft tissue to get to the bone. And it's a really big bone. So we're going to really need a very big blade. Bring on the dagger. Okay, I think you probably need some help. Shall we get another volunteer? Gentleman with sheep on the front, come down and help. And your name is? Isaac. So Isaac, you're going to have to help Tilly, if you would. So we're going to have to lift the blade at the front, please, Tilly. Now, I want you to be able to get through the soft tissue to get all the way to the bone so that we leave a mark. So moving forward gently. And you're going to push it. Aim for the bone. Can you get there? Push. Can you get in there? Almost. Yes. There we go. We've hit the bone. Thank you very much. Must be exhausted now. So if you pull this out, thank you. Thank you very much indeed to Isaac and to Tilly. So what we're going to try and do is we're going to take off the soft tissue into a bucket. Can you see on the side of the bone just that mark that sits there? That was the little nick on the end of the knife. So that when you have a stab wound into bone, then what will happen is you will just see a little bit of that end of the blade. And what we're going to do now is we're going to look at weapons that were around at the time of our body, and we're going to see what we can tell from them. So I'd like you, please, to welcome Emma Maudsley from the Royal Armouries. Thank you. A dangerous weapon.
Indeed.
So would this have been around at the time of our, I'm calling him a Viking, I don't care whether he is or not, but our Viking.
This is a reproduction of an axe, but very similar. Might have had a longer haft, but similar.
And you brought on some other weapons for us. So first of all, anything that can stab or can cut or can chop will leave us with sharp force trauma. So would you like to show us what happens if you put an axe, maybe not too hard, into the foam? There you go. Look how easily it went through. So that with an axe, we're going to get just a straight cut. And we're going to have, if you could imagine going deep into that cut, we're going to get a V shape because we're going to have the very narrow blade and widening towards the back. But with an axe, often you don't just cut once, do you? Yeah. You chop. Yeah. And so often with axes or something along those lines, we'd find multiple chop marks. So that's what we'd have with that. This looks like something a little bit dangerous inside the scabbard. And what is this?
So this is a sea axe.
A sea axe?
Yeah.
And so what I'd ask you to do with that is just cut the foam. And then, and what happens when you do that, if you turn it round, and you can see it very clearly in these, is that where you were cutting down, you've got a very, very smooth surface. But once you got down to the point that you were breaking through it, you can see that it becomes much more rugged and a bit more messy. You've got something else. And I know this is a ridiculous thing to say, but that's a very long arrow. And presumably, is this a normal sort of length?
Yes, this is quite a standard.
It's a standard length. So this one, does it have a name, this type?
Well, this one here is a bodkin. So
okay.
It's a similar but a different shape. So you have a different shaped head. This one has 4 sides.
So could we look at the shape that bodkin, did you call it?
Yes.
The bodkin causes. We want to get the tip of it in and see what kind of a pattern we're left with. What you get is a square shape, don't you? Yes. And I wonder if I could keep that one for just a moment.
You may,
Thank you. Could I ask you, though, when you leave, to take your axe with you, if you don't mind?
Of course.
Emma, thank you very much
Thank
indeed.
you.
Thank you. Now, if we come back to our skeleton, if we come to the skull, first of all, and I'm going to turn it round, so we go to the back of the skull and we go to the left-hand side. When I do that, can you see this area around here? That's an ante-mortem trauma. So this is a sharp force trauma, probably as a result of a blade, but he lived through it. He survived. Because we know that because we've got healing of the bone, because it's very smooth around the edges. So whatever caused that, maybe it was a blade, we don't know, but it's a sharp force of some kind It happened maybe even years before he died, but he was only 17, 18, 19 years of age when he did die, so it happened to him very young. And I want you to come right to the end here. Can you see a squared outline? Where did we last see a squared outline? We saw it on a bodkin arrow. I'm hoping you can see how it would have fitted in there, going literally into the skull there. I mean, for goodness sake, how unlucky is it that not only do you have a previous injury to your skull, but around the time of your death, what you also have is an arrowhead injury. So in your neck, you have 7 cervical vertebrae. And if we count down to the 5th, which is 1, 2, 3, 4, 5, I'm hoping that when I pull out the 5th cervical vertebrae, can you see another squared hole? And so that's another arrow. If that arrow has gone in to the left side of his neck, round about here, if you put your fingers there, can't you feel your blood vessels under there? Can you feel your arteries pumping? Huge arteries and veins in there. If the arrow has gone in there, the chances are that he's bled out, and the cause of death was an arrow injury to the neck. We can't say it killed him. It might be the manner of death, which we say it's a trauma, but it's likely that the one at the neck is more likely to have caused his death than is the one at the back of the head, because although it's pierced through the bone, it hasn't gone all the way through to brain tissue underneath. Now, if you remember, what we talked about was that there was a third thing that the anthropologist looks for. And what the anthropologist looks for is how many people are present. And I should warn you that it's connected to the grim reality of war, because he was found in a mass grave containing over 30 other bodies. And mass graves are particularly difficult to excavate, as the bodies can frequently become commingled or mixed. And I worked on the recovery of bodies from mass graves following the Balkan Wars. And in those graves, we might have in excess of sometimes 50 bodies in a single grave to excavate. But this mass grave, associated with our body, was found in the grounds of St. John's College in Oxford. And it was just simply as we were excavating to do some building. Now, if we go back in time, what we know is that there's an important source of English history, which is called the Anglo-Saxon Chronicle. And in the year 1002, very precise, King Ethelred the Unready, he was informed, so he had an informant that said that Danish mercenaries, now we can read that for meaning Viking, were intending to beguile him out of his life. So he'd been told that these Danish people were coming after him, and he was scared. So being afraid of this Danish threat, he sent out a mandate to kill all the Danes in England. And this became known as the St. Brice Massacre, and we actually know which date it happened. His date of death was the 13th of November in the year 1002. He was buried with over 30 other Danish men, very few of them elderly, all quite young, and the youngest was even younger than him. And when they were killed, presumably by the arrows as we saw, their bodies went into a mass grave, and they lay there undisturbed for 1,000 years until the builders came. And once the builders came in, we found them. Now, we know that he was a male. We know that he was a young man at the end of his teens. We know he was about 5'10" in height. We know he was Scandinavian. He was eating marine food. He was eating fish. And we've even got a date of his death. And we know that he was in good health when he was killed. We know that he'd had a previous fracture to his skull that he'd survived, probably caused by a blade. But we suspect from the 2 projectiles that we found, he had an arrowhead into the back of his skull, and he had another one into the front left-hand side of his neck. And that's probably the one that will have killed him. So coming in as he was as a pile of bones, we now know so much more about him. But there is one thing that we still need to know. Do we want to know what he looked like? Can I ask Professor Wilkinson, please, to come back in? Can I just say, she always gets the best lines. Right towards the end of any work that we've ever done together, what Caroline does is she recreates that face. And I have not yet seen the face, so I'm seeing this at exactly the same time as you. So I apologize unreservedly if I get ridiculously excited about it, because I'm looking to see the Viking for the very first time. Caroline, will you take us through what you found, please?
Yes, so we can see here this the skull from the two views so that we can see this healed wound on the back side of the head. The blue areas are the missing parts that we've remodeled. Then you can see the muscle structure and the skin layer in place.
And you can see the injury at the back there.
You can see the injury.
Wow.
If this was a forensic case, we would probably stop here. It probably would be black and white rather than colour, because we don't have the information about eye colour and hair colour and skin colour.
But you can do something a little bit more?
Yes.
Go on.
So because we've got information from yourself and from the archaeologists, we can add hairstyle, we can add facial hair that was suggested, and we can add clothing appropriate to this period of time from this part of the world.
Isn't that just amazing? He's darn good looking, isn't he? Our Viking from Oxford. So a young man at the end of his teens, a really young man. And suddenly, doesn't he look like a person? He started out as a pile of bones. I just think that is absolutely astounding. And I told you, she always gets the best lines. She always ends everything so incredible. Caroline, thank you for your talent. Hugely appreciate it. So in normal circumstances, if this was a forensic case, we would never assign a name to an individual, because the name that you have is the name that you were given. But we thought that in this case, it might be appropriate to think about a name that we could give for this individual. Now, he came and was found in St. John's College in Oxford. And we thought if we turned John into something that is a little bit Danish, maybe he might be content if we were to call him Johannes. So I'd like to introduce you to Johannes, who is the very attractive Viking from Oxford. Thank you very much indeed. So in this first lecture, what I've shown you is how I use my forensic anthropology training to restore identities to dead bodies. And in the next lecture, what we're going to look at is what happens when there isn't a body. How do we actually progress that story when the body is missing and we have to rely on other types of evidence and different forms of forensic science as we start to look to a crime scene? And the one thing that you will understand in forensic anthropology more than anything is that when we have remains in front of us, we have nothing but total respect, dignity, and decency for those that have passed before us. So I think the last thanks that I would ask you all to give is to Johannes. Thank you.
Details of organisations offering information and support are available at bbc.co.uk/actionline.